Thank you, Chair. First of all, I'd like to thank the organizers for inviting me to give the lecture. And I also would like to thank the organizer arranged the talks such that I don't have to talk a lot of different things, because the previous speaker had been mentioning a number of stuff that I like to talk about, so I don't have to spend a lot of time talking about it. So my title is Linking Process, that means manufacturing processing. And then the processing we change from microstructure, and of course will be you change the material properties. So it's quite different way to make material systems. And the one that I'm focusing on is the additive manufacturing through the advanced modeling. This is not a single person's job, so we have a lot of collaborators from doing experiments. I don't do experiments, but my people do experiments. So I learn a lot from the experimental input. And I like to actually say a little bit, I would like to call this experimentally consistent computational models, because there are a lot of things we don't know how to model yet. So I throw this question to you. But at the same time, by doing a lot of experiments, we understand a lot of the physics and how to tentatively model the system. And we need a lot of tools to actually come up with a way to do material modeling. So what I show you here will be most of our students, except Dr. Wei Xiong is a material scientist. He does a lot of the thermodynamic calculation for heat transfer for us in this case. And Jake Smith is here, and he will give the plasticity model this afternoon. So I want to give you a little bit about the background. I don't know how many of you know about additive manufacturing, and I want to compare what the conventional, what we call the subtractive manufacturing, SM, and the additive manufacturing, add materials. So the conventional material would be you make a piece of material, you remove material. That's the reason why we call it subtractive manufacturing. There are a lot of good things and bad things about this method. I just list here. I will not say too much about it. The additive manufacturing, would be is you add material. It's a very low waste in material, but it can really do a lot of complex geometry, and we want to incorporate topological optimization if possible. And of course, it's pretty well for repair components. And now, there are two types of additive manufacturing I'd like to talk about today. One is called electron beam, and the other one is laser beam. Now, so we believe that even though additive manufacturing is not really a new thing, it has been done for many years. Starting, you can think about using toothpaste, moving around. That's additive manufacturing. In fact, civil engineering done a lot of this for a long time. The biomedical does this a long time on this one here. But I believe would be combining modeling, you can do a lot more on this particular case. In particular, there are a lot of interesting applications that you cannot do with the traditional manufacturing techniques. Now, then what's involved? Involved will be design nanoparticle. We are focused mainly on metallic system, metals. So we need to design, particles. Basically, it would be powder. Okay. In medicine, powder has been designed so well they can actually go down to, really nanoscale. Right now, the powder we do are mostly in the micron scale in this case. So we do have a group led by Greg Olson working on design of powder on this technique. And I want to focus a little more will be how the design, the heat source model, and the process parameter. We talk about the powder size, how much powder the clusters hedge, the flow rate, the power on and off. I mean, you say E-beam on and off or laser beam on and off. And real-time sensing, this is something with the previous speaker talking about. Feedback control is very important in this case here. Of course, the pathway in this case. So all this process would really determine the microstructures. Okay, for example, voids, arc size, inclusions, phase fractions, and of course will be anisotropy, metrology, And this definitely, we can use a lot of classical plasticity model, but the thing would be you need to know how to calibrate the parameters, incorporate this process parameter in it. Now, in biological, for example, in dental industry, this has been done for a long, long time. You start with CAD model. That means you want the geometry you want to put in. You do a process, and you do some kind of calculations. You do a process modeling, and you determine the material properties, and finally you produce a part. So basically, this is a pretty standard procedure, but now we apply this to metal. In this case, it's not as easy as, like, say, a polymer or a certain kind of material in this case. So we designed this diagram called process structure property design. Give you one example what this is. This is basically layer by layer manufacturing. You can think about this like a printing system. You do one layer at a time. You program the shape you want. You move the system, and you can see they build up the structure. And faster, slower, it depends on how precision you want to do it. And then you can see would be become a shape. There are a lot of powder that you can reuse. You just remove them, and then you can reuse the system, and that's your part in this case. So this is layer by layer in 3D printing in this case. Now the other one is called the direct energy deposition, and that's the one most we will talk about today. And basically, it will be you inject powder to it, you melt it, and you just form the shape. And you can see this is a very simple illustration how this is being done. Again, would be the tube path is so important, and I think that is what the previous set would be, how you're going to use online control. And I think this is something that we can use a lot of these techniques on it. But of course, it will be this a lot more complicated than the traditional manufacturing process in this case. And this gives me my outline. I just give you some idea about the process structure property design, but based on additive manufacturing. And I will focus on metal base, and there's the method we're using, accumulation energy input. Basically, we need to design the heat source in this case. So I'll give you a little idea what it is. And then the computational process modeling for microstructure nucleation and evolution, because now you actually nucleate microstructure. And at the same time, because you are forming the system with heat on and off, you have not just nucleation, you have actual evolution in this case. So I'm going to talk about two-scale modeling, the micro heat source modeling, and then a macro heat source modeling, and how I'm going to put them together. And then the thing will be, we don't really know model everything yet, okay? But that's what we try to do. And we need to do a lot of experimental material characterization. So we want to identify what are the microstructure. And for this thing here, we're using informatic-driven design. Look at it. We basically based on image-based data collection, which we learn a lot from the digital 3D problem we have done. And we look at image-based mechanistic plasticity, and we started looking into the fatigue modeling. And the key thing is the image-based concentration law development. And finally, draw some conclusions. So let's give a quick review of the two different methods, the accumulative method and the energy input method. The active process will be direct deposition. We call LENS, laser engineered net shaping, or DMD is direct metal deposition. And the passive process is the powder bed. I'll show you both of them. We can talk about selected laser melting or the E-beam melting. Now, the energy input methods basically would be, we can talk about laser. In this case, you need to understand the photon beams, how the photon interact with the surface, collision, to generate heat, and that can melt. Okay? And then we talk about electron beam. It's the same, basically, but it's a little bit larger size in this case here. In this case, we talk about electrons in this case. Now, so what I'd like to say a little bit about additive manufacturing basically would be, we have two things, the powder supply and the energy supply. So if you lump the E-beam with powder, we call it E-beam melting methods. If you do the laser plus the powder, we call this the LENS method. And then you can do combinations in this case. Okay. In fact, you can combine both techniques. And this is something that would be a schematic diagram how this system is being built. And the E-beam melting, that will start with, you spread the powder bed, you preheat it, and then you use the focused electron beam, and then you melt it, and then you're using focused electron beam, and then you lower the platform. Okay. And then you can basically repeat 1, 2, 3. And the advantage of this would be you can do complex shape, you can control the microstructure, and you can design material using, for example, functional gradient material. But there are different ways to do this in this case. Now, let me give you a framework on this one here, based on this diagram we are talking about. Okay, and we started with the multiple powder falling powder or powder gas interaction. Okay, we are developing models for this. And I just show you the whole system. It's a little bit complex. Okay, and then this beam intact with particles. And then we propose basically looking at literature using Monte Carlo ray tracing technique to develop the melting process so they can actually come up with a mathematical model for the continuum modeling of the heat source. And then we look at micro and macro heat transfer with phase transformation, look at how this metal melting, remelting, solidification, and void formation and so forth, and phase volume fraction. And then we look for the larger scale is a solidification, phase change, and then of course will be after solidify the material characterization. And the final thing will be this a lot more the plasticity or material characterization aspect. And then you need a APL programming, integrate them all together so they can do online monitoring in this case here. So I'm going to just focus on lens entering process. Unfortunately, would be the process not as simple. That means you cannot model every single piece of information. You only model certain part of the information. The reason would be it's complex. And the other thing would be a small change in the process parameter. For example, the laser power, on and off, the laser speed, particle flow rate, hedge spacing, and layer depth. You have a drastic change in the final product performance. That means everything is going to change in this case. So the goal we look for here will be, we ask questions. Can the process parameter be incorporated into the mechanical performance and optimization analysis? And the goal basically would be we do multi-scale analysis, whatever it means in this case. Can this parameter be reduced? And the way we reduce it by informatic-driven decision and design. And finally, how do these parameters affect the material properties? We're going to do this using image-based plasticity modeling in this case. Let's just start with the heat source. Basically, it's a Monte Carlo from the method that we learned from the existing literature. We basically look at the electron interaction or photon interaction of the metal. And then you determine using Monte Carlo, get the energy distribution not on the surface only. I think most of the commercial code or most of the development right now is only on the surface. But if you really want to look at the metrology, we need to also look at the energy distribution in the depth in this case. And then we do curve fitting because you do that. Then you basically look at the curve fitting in both the plane and the depth. And you can see this, most people just do this part here, and we actually get the penetration depth in this case here. And that's our heat source model. And for this case here, we are not looking just at the radial distribution, we also look at the depth distribution of the heat source. And that makes a big difference in this case here. Okay. So the melt pool formation, actually there are a lot of physics that have been done that we can learn from the welding industry. Would be, you can say here would be we starting with the heat source bombarding on the surface, and this is the new heat source model that we come up with, account for depth. Okay, you start melting the system, okay, and then it can evaporate if evaporation starts. Okay, the molten liquid can increase the volume. Okay, and this would something called the explosion. Okay, In this case, eruption, then if you really look at the surface in a much finer scale, you can see these things actually happen. That's the model that we come up with, how we're going to model this particular metrology. I don't have time to go through how to design metrology, but that will be by itself, it's a different talk itself. Okay. Now the second thing will be, given this heat source model, now I'm going to program the path. Okay, you can see here will be, I want to do it in real time, direct energy deposition, and you program the path, and I want to see how the temperature distribution, the melting and remelting or solidification, because you go layer by layer in this case here. Okay. So this is basically will be, we need to have a very fast computation, online computation, so we can do online monitoring of the system. And so what we do here would be, in order to understand a lot more the melting and remelting and phase diagram and so forth, we actually do concurrent coupling. This is very standard. I think the first speaker talked about FE square. We do a similar thing, but this for heat transfer. So for this part here, you do a thermodynamic, we use the thermal count. Okay, and here we develop our own finite code, and all these coefficients are function of temperature, of course. And so the fine scale simulation would be, we look at melting, solidification, mass accumulation, volume change, and so forth. We solve a very simple equation, but they're concurrent coupled. Okay. And based on this would be, you can look for latent heat, you can look at the BCC, FCC, and then now you can look at the material parameter and also look at the microstructure evolution. Okay. Basically, we can say the formation of oxide, formation of micro voids and larger voids and so forth. This is something we want to do predictions. The prediction is prediction, but you need to do calibration. So basically, it would be when you change your process parameter, everything will change in this case. And one important thing is the dendroid rate. Okay, so this is a lot to do with the cooling rate, and you can see here will be experimentally with different cooling rate, you can different dendroid armament. Okay, so this you can predict it by phase field calculation, and our colleague Peter Voorhees is pretty well known in this particular size. And of course, you can also look at the grain size in this case. So we want to put all this in the model for the characterization aspect on it. I'll just give you some estimation. For example, would be the black line here is using experimental calibration, whereas the red line is using the prediction. Of course, you can see the peak is quite different, but the time snap difference are reasonably good. But this is a lot more on how detailed you can model this particular system in this case. You can also look at the fraction of solid, the fraction of BCC and FCC, but this one is mostly on steel particles, so it's much simpler, just BCC and FCC one fraction. And now you can actually compare the two results with the thermal count derived properties and also the experimentally derived properties in this case. They're reasonably good, but of course you don't expect them to be matched completely. I think that is something that we need to get a lot more understanding what is missing, what is not missing in this case. Now, so we formed a part, so after process. Now, the question would be, in real life, you want to do a very complicated system, but in actuality, can I design some simple experiment? Okay, you can think about would be in real life, you talk about big size, but when you talk about doing characterization, you talk about maybe millimeters, very small. Okay, because usually powder width we are talking about is about 0.1 or even less than 0.1 millimeter per layer. So if you try to build meter, it's a long, long way. Okay, but when you try to build this 0.1 millimeter length, you talk about many layers, thousands of layers. Do I need 1,000 layer of particles, okay, to really characterize a system? So this is something we need to figure out will be what kind of simple experiment that we can design so that I can use a very limited number of layers to characterize the performance of the whole system. Now this what we learned from D3D would be for fracture. Okay, the question would be how many particle I need to understand. I think Professor Needleman is very well known in this aspect here. How many particle path I need to understand before I can predict, say, meter of fracture. Okay, so same idea in this case here. So what we did here will be we make specimens. Okay, this is we haven't really decided what's the best way to do it. We make specimens, say like this, for a tensile specimen. We look at different regions. You can see they're very, very different microstructure in this case. And we look at around the fracture surface. Look at 1, 2, 3. Okay, so you can see here will be this is the bottom one. This is the top, near the fracture surface, and this is the top one, and they are completely different. The number of voids, they're different. The void area fraction. So we are talking about mostly with the area to volume fraction to determine the material properties in this case. And you can talk about with the void and inclusions, arc size. They will change a lot for the fatigue properties. Of course, the grain orientation. All this has to be accounted for. And you can think about what would be the anisotropy would be you build up a piece of material, you cut them up in different directions, and you get different parameters. Right? So how are you going to minimize this on this type of parameters? And of course, there will be, you can do the same thing for the fatigue, tensile test, and so forth. Now, what we base on here would be we do both experiments and simulations. We do a lot of data collection. We are still collecting data. We're going to store the data, just like the previous speaker talked about, data processing, and develop theories. And our goal here is to do image-based because we learned so much of this image-based. And not only that, what we do image-based is pretty expensive, so we develop method will be from a few 2D image basis, assuming statistics good enough, we come up with a reconstruction algorithm for three-dimensional microstructure in this case. So different techniques we are still learning about. The key thing here is the 2D images to reconstruct 3D statistical representation in this case. Reduce order model. So previous speakers said a lot. We can learn a lot from there, but we have our own. We start the online, basically the real calculation. This is a test specimen we're talking about, and the offline is a lot more on the 3D image reconstructions. And then we create database, and we do both elastic and plastic DNS, do a lot of calculations. But we use micromechanics-based method to solve this problem. We do data compressions, just like image processing, so that basically we can use a micromechanic base, which is mostly linear elastic, okay, to look at the area of interest, okay, or the clustering method, and then we do a data compression. Okay, so the data compression basically would be what's the minimum number of regions that I need to define so that I can do a much coarser mesh calculation to do it. Okay, and then this is the micromechanic clustering analysis. It's a lot more green function approach analysis on it, and then we do curve fitting. Okay, so this curve fitting will be again this equation we're still writing a paper on it is derived based on different micromechanics equations. And then you go back and forth in this case. I'll give you some idea how it works. Just give you a 2D problem. You're going to write the local. You can think about the local strain is more or less the Gauss form, and the macro strain is a far field solutions. And you do a lot of RVE calculation. But we want to do this RVE calculation for different type of testing that you want to do. And you come up with this matrix, the mapping matrix between global and local, okay, and then you come up with your data format, lots of data in this case. Okay. And then again, will be all these are based on image base, so we do a lot of data. But this image base would be a function of process parameters. So you can see it would be for one process you have one set data. And then we basically will be do statistical reconstructions, look at the micro structure placement. So these are something that we are still working on. Okay. And I think in this case, and now you're going to come up with your plasticity model, and Jake Smith would talk about this afternoon in here. And the whole idea would be Those models are pretty well established. We use a lot more on the GTN model, but it's modified with anisotropy and so forth in this case. Now for calibration procedure, like I said, there are different microstructure we need to look at. Okay. And then, say for example, for damage evolution model, pretty standard nucleation, growth, and shear. And then you basically come up with this distribution and you calibrate your specimen. For example, would be for tensile and shear, actually this is the one that we need to design an experiment or something like this. Okay? And they do a lot of specimen testing. The question will be how big the specimen you need, how many layers. Okay. The current focus now will be, I have just a couple of new students working on look at fatigue. So we actually monitor how the void growth is a fungal cycle, and then look at the microstructure driven on it. And for that, we need to do crystal plasticity. And this is something that we have done for the two oxide with a void in between. And I think my time is up. So I just give you the challenges. It's a pretty complex multi-physics and multi-scale problem. It's very computation intense. It's data collection, storage, processing, and along that, we need to develop theory. And opportunity is tremendous if you can understand all this because it can apply to a lot of different kind of manufacturing processes. Thank you.
Thank you.